In September 2017, thousands of miles above the swirl of Saturn's cloud tops, a machine worth $3.4 billion was screaming through the upper atmosphere at 34 kilometers per second. For 13 years, the Cassini spacecraft had been humanity's eyes and ears in the outer solar system. It had revolutionized our understanding of ring dynamics, mapped dozens of alien moons, and redefined what it meant to explore deep space. It was, by almost every metric, one of the greatest engineering masterpieces in human history. And yet its final command did not order it to return home. It did not order it to park in a safe, eternal orbit. It ordered Cassini to die. Within minutes of entering the atmosphere, Cassini's thrusters fired at 100% capacity, desperately trying to keep its high-gain antenna pointed toward Earth. But the mechanical strain was too great. The spacecraft began to tumble. Friction turned titanium into molten liquid and structural beams into vaporizing plasma. As the telemetry signal flatlined on the monitors at JPL, Cassini was dissolved into atoms. This was not an accident. It was a planned execution. And Cassini is not alone. In recent years, NASA has ordered probe after probe, machines that cost billions of dollars and took decades to build, on deliberate, high-speed suicide missions into Jupiter, Saturn, and beyond. Why would the world's premier space agency intentionally incinerate its own crown jewels? The answer is not a lack of money. It is not an engineering failure. It is a terrifying realization about life on Earth and a desperate race to preserve a secret that hasn't even been discovered yet. To understand why we must vaporize our greatest machines, we first have to talk about a fundamental truth of biology. Terrestrial life is terrifyingly resilient. Before any spacecraft leaves the clean rooms at Cape Canaveral or JPL, it undergoes an aggressive, multi-layer sterilization process. Technicians scrub hardware with isopropyl alcohol, bake components in specialized heat ovens, and bathe sensitive electronics in intense ultraviolet light. They wear sterile suits, masks, and gloves, working in air-filtered environments, cleaner than an operating room. Yet, despite our best efforts, absolute sterility is an illusion. Meet the Extremophiles. Microorganisms like Bacillus cephensis or Deinococcus radiodurans do not merely survive in extreme environments, they thrive in them. In laboratory tests, these microscopic organisms have been frozen in liquid nitrogen, irradiated with gamma rays thousands of times stronger than lethal human doses, starved of water, and exposed to the vacuum of space on the exterior of the International Space Station. When the exposure ends, they wake back up. When a spacecraft like Cassini or Juno launches, it carries billions of these invisible stowaways. Tucked deep inside the crevices of circuit boards, trapped beneath thermal blankets, or shielded within the interior of unburned propellant tanks, these spores go into a state of suspended animation. They endure the vacuum of space. They survive cosmic rays and solar radiation. They endure temperatures near absolute zero. And that presents NASA with a catastrophic mathematical problem. If you leave a dead, unpowered probe in orbit around a gas giant, its orbit will not remain stable forever. Over centuries or millennia, gravitational perturbations from surrounding moons will eventually tug on the derelict spacecraft. One day, the math catches up with you. The probe will lose its orbital balance and crash into a moon. If that probe impacts a cold, dead rock like Mercury or our moon, the risk is minimal. But in the outer solar system, the targets are not dead rocks. They are pristine aquatic biospheres. For most of the space age, scientists believed that the search for alien life was restricted to the Goldilocks zone, that narrow band around a star where liquid water can exist on a planet's surface. Mars was the prime candidate. The outer solar system was assumed to be a frozen wasteland. Then came Cassini, Galileo, and Voyager. When Cassini arrived at Saturn, it turned its sensors toward a tiny, snow-white moon named Enceladus. What it found stunned the world. Beneath an icy crust, tens of kilometers thick, lay a global, liquid water ocean. Tidal forces from Saturn flexed the moon's interior, creating geothermal vents on the ocean floor, environmentally identical to the deep-sea hydrothermal vents on Earth, where life may have first originated. Even more incredible, Cassini flew directly through giant geysers erupting from Enceladus' south pole, detecting complex organic molecules, salts, and hydrothermal activity. Over at Jupiter, the Galileo probe revealed a similar secret beneath the cracked, icy surface of Europa. An ocean containing more liquid water than all of Earth's oceans combined, warmed by tidal flexing and kept liquid under perpetual dark ice. These moons are the true sanctuaries of our solar system. They possess the three core ingredients for life: liquid water, an energy source, and organic chemistry. Now imagine what happens if a dead probe carrying millions of dormant Earth microbes crashes onto Europa or Enceladus. The energy of the impact shatters the outer ice crust. The heat generated by the probe melting into the ice, combined with the residual radiation from its plutonium-238 radioisotope thermoelectric generator, creates a local pocket of warm, liquid water. The stowaways wake up. A single terrestrial bacterium introduced into a global ocean with no natural predators and abundant chemical energy could replicate. It could contaminate an entire ocean. It could outcompete native alien life forms, causing an ecological extinction event before humans even know alien life exists. Or worse, 50 years from now, a dedicated life detection mission lands on Europa, drills into the ice, and finds living cells. The announcement shakes the world, only for scientists to realize years later that they didn't discover alien life. They discovered Earth bacteria that we accidentally dropped there in 1998. This is the nightmare of forward contamination. And to prevent it, space agencies operate under a strict framework known as Planetary Protection. When viewers watch probes like Cassini or Juno meet their violent ends, a natural question arises. Why can't we just reuse them? Why not refuel them, park them in a safe orbit, or salvage their billion-dollar electronics? To answer that, we have to look at the harsh realities of deep space mission architecture. First, there's the problem of fuel. Deep space probes do not carry infinite propellant. Every gram of hydrazine or nitrogen tetroxide launched into space requires kilograms of rocket fuel to lift off from Earth. By the end of a multi-decade mission, a probe's fuel tanks are virtually empty. Without fuel, controllers on Earth lose the ability to control the spacecraft's trajectory. A probe without attitude control is an unguided missile waiting to collide with something. Second, there is the environment itself. Jupiter, for instance, possesses a magnetic field 20,000 times stronger than Earth's. It traps charged particles, creating a radiation belt so intense that it fries electronics, degrades silicon chips, and breaks down structural materials. When the Juno spacecraft entered orbit around Jupiter, it was encased in a titanium radiation vault to protect its brain. Even so, every orbit through Jupiter's radiation belts inflicts cumulative, irreversible damage. Electronics degrade, sensors go blind, solar panels deteriorate. By the time a spacecraft reaches the end of its primary mission, its hardware is exhausted, irradiated, and running on borrowed time. Trying to park a dying spacecraft in a high, stable orbit sounds reasonable in theory. But space is crowded with chaotic gravitational interactions. A probe parked in a safe orbit today could have its trajectory altered by a gravitational flyby of Titan or Ganymede 50 years from now, flinging it straight into an ocean moon. Refueling a probe at Saturn or Jupiter is currently physically impossible. Bringing it back to Earth requires more energy than the probe used to get there in the first place. When faced with a choice between parking a degraded, uncontrollable probe near liquid worlds or destroying it completely while we still have control, the choice is absolute. The decision to destroy a probe is not viewed by engineers as a tragedy. Instead, it has been transformed into one of the most brilliant tactical maneuvers in spaceflight history, the grand finale. Instead of simply wasting the final descent, NASA scientists turned the probe's death dive into an unprecedented scientific opportunity. When Cassini was commanded to plunge into Saturn in 2017, it was sent into the narrow, unexplored gap between Saturn's upper atmosphere and its innermost rings, a region no spacecraft had ever dared to enter due to the risk of destruction. During its final 22 orbits, Cassini sampled Saturn's gravitational and magnetic fields with extreme precision, determined the exact mass of the rings, and tasted the planet's upper atmosphere directly. In its final seconds, as friction tore away its insulation, Cassini turned its mass spectrometer directly into Saturn's sky, beaming back real-time chemistry data about the gas giant's atmosphere until the very moment its antenna lost lock with Earth. It gathered data that was physically impossible to obtain during any other phase of the mission. It turned its execution into its ultimate scientific breakthrough. This protocol is now built into the very DNA of deep space exploration. When NASA's Europa Clipper mission reaches the Jovian system, its trajectory and mission profile will be governed from day one by Planetary Protection protocols. When its mission ends, it will not be allowed to drift indefinitely. It will be commanded to crash into the radiation-seared, barren surface of Jupiter itself, or a dead moon like Callisto, ensuring Europa remains untainted. The same fate awaits Dragonfly, NASA's rotorcraft mission to Saturn's giant moon, Titan. Every dollar spent, every titanium bolt machined, every line of code written for these multi-billion-dollar flagship missions accepts a fundamental premise. The hardware is disposable. The science and the integrity of the cosmos is sacred. Human history is filled with stories of exploration marked by unintended destruction. When terrestrial explorers crossed oceans to new continents, they carried diseases and invasive species that reshaped entire biospheres, often extinguishing unique ecosystems before they were fully understood. In our journey into the cosmos, we have resolved not to repeat the mistakes of our past. The deliberate destruction of Cassini, Juno, and the probes that will follow them is more than an engineering compromise. We sacrifice our greatest mechanical gravels, vaporizing billions of dollars of titanium, gold, and silicon in distant alien skies, so that when we finally do find life in the dark ocean of an alien moon, we can look at it, measure its DNA, and know with 100% certainty that we are not looking into a mirror. We are looking at a second Genesis. If you enjoyed this deep dive into space exploration and mission architecture, hit the like button, subscribe, and leave a comment below. What do you think? Is destroying these probes the right moral choice? Or should we be finding ways to preserve our history in space? Thanks for watching, and we'll see you in the next exploration.